Hey, Megami. So I got some of this working off camera. Just to remind you, what we're doing is I want in my head, what I'm like, my goal is to construct a package through Singular, which is a computer algebra system, and Singular has a Julia interface. So I want to construct basically a Julia package, which allows some operability with central simple algebras. So what we have so far is we have a type, which is a central simple algebra, and basically given a ring and an ideal, so a non-commutative associative ring, and an ideal in that ring. This can define a central simple algebra, and then you also need to kind of specify the degree, and the type just keeps track of those three pieces of data. We have a function, simple algebra, which constructs the algebra that you would get from units A, B inside of a field, along with a root of unity and of some degree. This function calls the exact same thing, it's just a different case. And then we have a function tensor product, which creates the tensor product of two central simple algebras. So if we have one object A, central simple algebra, and another object B, central simple algebra, I got it working so that we can just input those and then we get as an output central simple algebra. My kind of desired functionality for this program, or packages associated, or this package, would be, say, to input a central simple algebra and to be able to determine the index and the exponent of that algebra. I'm not totally certain that it should be possible to do this. So I think there's one paper that I can think of where determining the index may be possible. So over like a kind of iterated Laurent series field, there's some way to determine the index of an algebra. And of course over number fields, you might also be able to determine the index of an algebra just from knowing its relation with the exponent or the period. But the exponent is the one that I really have some hope for. So the index seems like you probably won't be able to do this in general, just because what is the index? Well, it's the kind of the GCD of all closed points on a certain variety, so every Brauer variety. And so if you have just any given algebra, you can ask, does it have index 1? And that's equivalent to asking, like, is the associated set every Brauer variety, does it have a rational point? So in general, you know, given some collection of polynomials, hard problem to determine if it's got a rational solution. So I'm not optimistic about that, but I think that the exponent, maybe there's a chance. So let me go grab my notebook. Another thing that we could do is, I was thinking about this recently, is that we could implement some cohomology calculations for central simple algebras. So I've never really thought about the Hochschild cohomology of algebras. But this is something that it's possible to think about. And so we could do it. My window manager's kind of acting up. Let's close out of that. Let's drag this over here. Let's make sure that this is still running. And now let's pause because I have to organize this again. Okay, we're gonna close this, and we're going to put that there. Make sure OBS is still running, which it is, but not where it should be. So we'll just switch like that. Yeah, for some reason the tiling manager has been buggy, to say the least, on my desktop recently. So I don't know what music I want to listen to, right? I mean, this isn't bad music, but it's definitely gonna get copyrighted or something, right? Kind of is bad music too. Ah, it's fine. Okay. If I go back to tiles, does everything mess up? Not necessarily. Okay. That wasn't really the problem though. It was operating like this. Alrighty. So what does the Hochschild homology, cohomology tell us about an algebra? So I'll try to figure that out because this is something that could be computable, is what I would expect. If anything, I almost expect that there's already a package that will compute this for an algebra. Right, so Hochschild homology is homology theory for associative algebras over rings. There's also some theory for functors. Let's not worry about that. K is going to be field. A is an associative algebra. M is a bimodule under A. The enveloping algebra of A is the tensor product of A with its opposite. That's just for us going to be a matrix ring. Bimodules over A are essentially the same as modules over the enveloping algebra. So in particular, A and M can be considered as A to the E modules. Hochschild homology and cohomology are defined to be Tor and X functors with, okay, so you write it as Tor AM. So that's like if you're taking A tensor M under this enveloping algebra, and then taking higher tors of this. So I'm not exactly sure how. I guess the enveloping algebra admits an action on A through the left when you have A, and through the right when you have A op. Okay, and then M is just a bimodule. So that makes sense. If we let K be a ring, A an associative K algebra, that is a projective K module, and M an A bimodule, right? A tensor N for the n-fold tensor product. And then the chain complex that gives rise to the homology is just taking M with tensor products of tensor powers of A and then having some differentials. So D0 is special. Oh, they're all... No. Why are they writing that? So we've got D0 in degree N doing something, DI in degree N doing something, and DN. So they're just pulling out the D0 and the DN because they will be, I guess, not of this form. Okay, so then we take Bn to be this alternating some of these DIs from I equals 0 to N. And then this is differential, it gives us a chain complex. Right, there's some simplicial way to think about this. Not so important. There's a similar looking complex called the bar complex, which formally looks very similar. In fact, the Hochschild complex can be recovered from the bar complex. You know, another thing that might be useful to think about is emitter cohomology. And I think this gives you some way of describing the Brouwer group. Yeah, so I think that this gives you some way to describe the Brouwer group, but is it a nice way? Because one thing that you do want to know is basically how would you... Right, so we're trying to figure out if we have essential symbol algebra, how do we tell if it's got a trivial Brouwer class? And so realizing kind of a class in the Brouwer group is a first step. The few ways that I can think of doing that are not particularly helpful because they don't seem to admit kind of algorithmic resolutions for determining if the corresponding class is trivial. And the emitter complex is one that I haven't thought about before. So that's on the table. The examples of Hochschild homology computations can be stratified into a number of distinct cases with fairly general theorems describing the structure of the homology groups in the homology ring for an associative algebra. For the case of commutative algebras, there are a number of theorems describing the computations over characteristic 0, yielding a straightforward understanding of what the homology and cohomology compute. In the case of commutative algebras, the Hochschild homology has two main theorems concerning smooth algebras and more general non-flat algebras. The second is a direct generalization of the first. In the smooth case, for smooth algebra A, the Hochschild constant Rosenberg theorem states that there's an isomorphism between Hochschild homology of the algebra and the nth sheaf of differentials. Okay. To some extent, I knew that there was this relation. What does this tell us about our situation? The commutative case doesn't tell us really anything about the situation for associative non-commutative algebra, but it might tell us that we should expect somehow smoothness to be related. If we can make sense of smoothness for non-commutative rings. So one simple example is to compute the Hochschild homology of a polynomial ring, then generators. Product structure is given by some stuff, and what you get out of it is the polynomial ring back tensored with the free antisymmetric algebra over Q and N generators. Oh, and the differentials, dx1 to dxn, free antisymmetric algebra. So this is just the exterior algebra on N symbols. And antisymmetric means that A times B is minus B times A. No, yeah. Yeah, that's right. Oh yeah, A times B is minus B times A. Yeah, and then this is not so clear, but since you're in characteristic 0, it's the same. I guess maybe that is actually... No, since you're in characteristic 0, it's the same. Yeah, sorry. Okay, commutative characteristic P case. I'm not so interested in that. You get some crap. Kind of want to say fuck this. So what's this going to do for us? So in the characteristic P case, there's a useful counterexample of the Hochschild-Cosine-Rosenberg theorem, which elucidates for the need of a theory beyond simplicial algebras for defining Hochschild homology. I hate when people say shit like that, but let's see. All right, so consider the Z algebra FP. We can compute a resolution of FP as the free differential graded algebras. So Z goes to Z by multiplication by P, giving the derived intersection. FP tensor over Z FP. It's FP adjoint E mod E squared. Degree of epsilon is 1, and the differential is the 0 map. Just because we tensor the complex above. In order to compute this, we must resolve FP as this kind of algebra. Observe that the algebra structure forces epsilon to go to 0. Then because we have to resolve the kernel, we can take a copy of this, shift in degree 2, and have it mapped to that. The kernel in degree 3 epsilon times this thing equals this thing. We can perform this recursively to get the underlying module of the divided power algebra. The algebra structure comes from the general theory of divided power algebras and differential graded algebras. Note, this computation is seen as a technical artifact because the ring FP adjoint X is not well behaved. For instance, X to the P equals 0. One technical response to this problem is through topological Hochschild homology. I just hate when people say one response to this problem. Mainly just because you have to so maybe I just don't see what the problem is, but like usually if there's a definition, then it's not a problem. It's just how the definition works. So you'd have to explain like that you have an external goal that this is problematic to, right? You have to say like it makes sense, for example, if you're saying something about the Weil cohomology theories, and if you say something like it's been long enough that I can't even remember what kind of problems arise from this, but it makes sense that if you say something like, let's say just for the Weil conjectures, and you want to prove some kind of Riemann hypothesis type statements in characteristic P. Well, you can't simply use singular cohomology. It makes sense why you can't do that for varieties over finite fields, and so there's a genuine problem there. But in this case, there's nothing that exactly we're trying to prove, so there's no problem, right? It's just a facet of the definition. The above construction of Hochschild complex can be adapted to more general situations, namely by replacing this. Is not something that I want to think about either. So The one thing is that Hochschild cohomology has some kind of relation to deformations of algebras. So I'm trying to figure out, just in general, like, is Hochschild homology all field independent in some way? Is there some information or some structure there that will tell us, like, I don't know, I almost can't imagine it. So let's go back and see the definition again. Let's see, open this up too anyways, but let's go back and look at the definition. Okay, so we define it as just some Tor. So in no way is that ever going to vanish, right, if we go up some field extension. So if we're looking to apply this to central simple algebras, then it's not going to be so easy to just discern from the structure of some of the dimension of this thing. So I mean, so what we're looking for is some kind of invariant that's computable that will tell us when our algebra is trivial in the Brauer group. And the exponent is a good one, probably. We just want to look for how we can actually compute it. And I've never seen any kind of reference to the exponent through Hochschild cohomology or homology, but I was just thinking maybe this is computable, so. Okay, and then there's probably no other thing of interest in here, really. I mean, maybe we could do, instead of, I was gonna say, maybe we could do a free module for A, and then for M, just do the ideal that defines the ideal that that defines the algebra. Would that be an interesting thing to do? Maybe if A is free, then there's some kind of computation, easy computation that says that's a stupid thing to do. So let's look up Hochschild cohomology of free associative algebra. Hochschild cohomology of free associative algebra and ideals. I don't know. Yeah. What do we get here? Yeah, so the one thing that would make this interesting, right, is that basically if whenever we have free associative algebra and an ideal defining a matrix algebra, if that just tells us something automatically, and otherwise it doesn't. And would we expect something like that to happen? Well, it's certainly not clear, I think. And so, all right, now we go to Gemini, which is kind of more efficient search. We've got Pro because of the phone upgrade. So we'll ask Gemini, hi Gemini, and we ask with hello because it told me to obey last time I asked it questions, which was freaky. So, hi Gemini, do you know anything about the Hochschild homology? Or cohomology of HHN AI, where A is a free associative algebra. I is an ideal. See if it says anything about this. Then we think of some alternatives in the meantime. So I had one idea originally, which was that basically you have to look for a certain module inside of, you have to look for a certain module under your algebra, right? Being a matrix algebra is exactly that, you have a minimal or a module of some smallest possible dimension, granted the degree. And you could try to randomly generate these, but because they're sparse inside of, you can try to randomly generate these from ideals, but the minimal ones are sparse inside of the space of all ideals. So it's not exactly a good, it's basically not exactly a good way to go about trying to find out what the index is of an algebra, or which would tell you if it's trivial or not, split or not. And so we want to get around that somehow. Okay, so for free algebras, free associative algebras, higher Hochschild homology or cohomology vanishes. So HH0 is the abelianization. Is that what you'd call this for an algebra? Quotient of A by the subspace spanned by commutators. This is often called the space of zero cycles, or the trace space, okay? HH1 is A tensor V, where V is the K vector space spanned by the generators. And the map D is given in this way. Almost looks kind of like a bracket of some kind. And for n greater than or equal to 2, it's 0, okay? Great. How does this relate to the ideal? So we're going to use some short exact sequence. And then in general, HH0, this is upper. Upper is derivations mod inner derivations. So this already, let me think. Maybe you could say something about the space of derivations. So if you were looking at just derivations from A to A itself, then I guess that these are all inner. And so that would be 0. So for any central sum algebra. Okay, so not useful. So, but for I, it's not so clear. Be dependent on I and A mod I. Okay, and higher Hawkshead cohomology is 0 for any bimodule. So that was kind of the thing maybe that I was expecting. So let's look at this, right? So we got some long exact sequence, So this one's always 0. So basically HHN of A comma I is the same as A comma A mod I. Great. For n equals 1, we've got some sequence HH2, HH1, 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 HH0. Since HH2 of AA is 0, we get some isomorphism here. And now we can think about this one must be one of these is off, right? So HH2 of AA is 0, which means that HH2 of AI is isomorphic to HH3 of A comma A mod I. But HH3 is 0. No, that's not true. That'd be some duality here. Yeah, so it's not this. So this statement's not so. I mean, not so true, right? Where did I scroll past it? Oh, I was here. No, maybe I skipped some stuff. All right, give me a second. I mean, this is seemingly not true. There's a shift in grading that needs to happen here. So one of these, specifically, this one should have a degree 1 higher. And then for the case of 1, this again should be 3. But we do have that HH1 of AI and HH2 of A mod I are related. So HH2 of A mod I embeds into HH1 AI, and that goes to HH1 AA, which Gemini says is this space. So kernel of this D map. We use a K vector space, and we have this differential. That's just whatever it is, isn't it? This kind of feels like polynomials, and then so so for example, like polynomials in xi, tensor xi, that is seemingly the only thing that I can imagine actually commuting. And then so when you have just a fixed xi, and then when you take linear combinations, okay, so something happens. So this is some non-trivial gadget. And HH0 it's not saying that the space of commutators is an ideal. It's not saying the ideal generated by commutators, so that's some non-zero thing too, I guess. So HH1AA is something, and HH0AA is something, and HH1AI and this thing, not so clear. For n equals 0, this is I mod A comma I, where AI is the submodule generated by elements that look like brackets. Hochschild cohomology for HHN. Okay, so the fact that HHN is 0 for any bimodule. Right, we get vanishing for all n greater than 2. For n equals 1, we get some crap. And for, how does this tell, what does this tell us? So they just replaced it. So HH A and A, that's Z A, and outer derivations. So in our case, it's going to be 0. And the center of A is just going to be K itself. HH0 of AI is all of those elements such that A times I is I times A for all A and A. Center of the ideal as an A bimodule. Well, K is not in the ideal, and so this should be so this should be just 0, I guess. And so this thing will always contain K, but then we'll have the HH1 term, which will sit in between 0 and this thing. So this is going to be the center of A mod I or something like that, which is the center of the ideal I as an A bimodule. So if it was an analogous formula, right, that HH0 of A mod I was the center of A mod I as an A bimodule, then I think the center would be K again. And so that's not so interesting, is it? And then HH1 of, what was that last one? HH1 of A mod I must be 0 if the outer derivations are 0. Okay, so that's not so interesting. And then what's it say after this? So the role of H unitality in relative homology. Description for n greater than or equal to 2 in terms of HHN raises the question of how to compute the latter. Yeah, so in general it's true that there's some interactions here, but for such some algebras it seems like we won't get shit. So we're kind of back on the grind of trying to figure out something computable for an algebra. So, one of the things that's annoying in this case is, okay, so the index is, there's an internal property that describes this And you think that that would make it computable from this perspective, but because of the sparsity of these modules inside of the space of ideals, it doesn't work out. What about for the exponent? So the exponent, right, we just want to determine, find an algorithm, see if something is 0 in some group. I think there's an algorithm for doing this for divisors. So like if you have a divisor, then there's an algorithm for determining if there's a linear equivalence with 0. So maybe we just ask Gemini this too. I mean, Carl Schweid has a program Macaulay too that you can check if two divisors are linearly equivalent. So how does that work? We could probably look it up in the interim. So here's the archive post that tells you about it. So linearly equivalent. We also include code for determining whether divisors are linearly or Q-linearly equivalent, and for checking whether divisors are Cartier or Q-Cartier. Yeah, how would you figure that out? Unraveling the enigma of principal divisors, an algorithmic perspective. Yes, there is an yes, algorithms exist to determine if a V divisor is principal, but their complexity and feasibility depend heavily on the nature of the underlying variety. At its core, blah, projected space curves toward varieties, the general case computational software. Macaulay 2 prominent software is principal. This function directly tests whether the V divisor is principal. It is linearly equivalent. Yeah. This is what I just said. So the algorithms underlying these functions are sophisticated and often involve Grosvenor basis computations to work with the ideals, defining the subvarieties in the divisor, and to compute the space of global sections of associated line bundles. The essential idea is to compute the vector space of global sections of the line bundle associated with the divisor. The divisor is principal if and only if the space is non-zero, and for any non-zero section, it is the divisor of that section. Oh, okay. So what you do is, so like, let's say we're working on a projective variety, right? And okay, so it's not entirely easy to figure out the space of global sections always. But if we're working with a divisor, then we can just think about it as, so like, let's say we're working with a projective variety, we've got a graded ring. A nice graded ring, let's say. Then Okay, well, if we just had a commutative ring, so in the affine case, then we'd be looking at kind of combinations of height 1 prime ideals or fractional ideals. How would we go about implementing this? So the easiest way to get a divisor is to write down an ideal whose support is all height 1 prime ideals, I guess, and multiples of a divisor in that case. Can be thought of, I don't know if you can think about it as having like powers of the ideal, or whether you need to specifically, I mean, so like this is not an optimal way to do this, but right, if you take some ideal, defining a divisor, I want to say that it's well, in the affine case, if you have some ideal defining a divisor, I mean, that ideal is a fractional ideal, and so you can do some arithmetic with fractional ideals to try to get like sums and products. Once you have an ideal computing the space of global sections, in the affine case, it's the whole thing. But if you are looking for the graded case, then you actually have to do some amount of work. So I've never read about graded fractional ideals. I wonder if that's a thing. This is some ideal quotient to get to is it the same for a graded ring? So okay, well, let's say, okay, if we have a module for a graded ring, then it's defining a line bundle if and only if its like associated sheaf is a line bundle. So it's gonna be quote unquote like a invertible module up to torsion, I guess. There's a little bit more in there. Okay, the global sections, though, they should just be the degree 0 piece of some homogeneous. So they should just be the degree 0 homogeneous elements inside some graded module. Ideally. I'm not sure how you'd do this if the module is not nice enough. Then the divisor's principle, if and only if this space is non-zero and for any section. So then you just have to take any element, and we'd want to check if the divisor that we have is minus div s. To find the divisor of S, I think you just have to take some... essentially, I think this is where you have to somehow kind of compute valuations of S at different heighted primes. So if you knew kind of already like what primes were supporting D, for example, then you can just take for each prime inside of D, you look at the valuation of S at that prime, which I guess there's some algorithm for computing that. And then you say yes or no, do you get the same kind of integer from D and then valuation from S on the side. Okay, so there's some definite haziness in there about how you actually go about doing this algorithmically, but I can see that there's some amount of algebraic geometry and commutative algebra that would allow you to do this. My hope was that, well, there's this sequence, the Picard-Brouwer group sequence, and I was thinking maybe you'd be able to utilize this. So for like a function field, you can kind of relate the Picard group of variety X to the Brouwer group of X and the Brouwer group of the function field. That might be one of the only ways that I actually can see this going well. So, okay, what am I talking about? Brouwer, Picard sequence. So there's a exact sequence. I actually feel like it's probably better just to pull up Danny Krashen and Michel Shapiriani. I don't know how to spell that name though. Shapiriani. This relative Brouwer groups for genus 1 curves. So the sequence looks something like, yeah, I mean, it looks something like this. So let's just find it in here. So this is the sequence that I was thinking of. So we've got that the Picard group of X includes into the K points of the Picard scheme of X. So X here is a variety defined over K. Let's assume it's very smooth, geometrically integral. It's nice as you can have. And then there's a map from the Picard, the K points of the Picard scheme into the Brouwer group, taking a point to the class of some essentials of algebra. And so how you think about this is that if you have a line bundle on X over an algebraic closure, that defines some map from X to a Severi-Brouwer variety. So put over algebraic closure, it's just a projective space. Line bundle defines a map from X to projective space. And then kind of the Galois invariants of that map give you this K point. So it sends, or kind of goes down to the rational base field. And this thing is basically saying, okay, well, you take the line bundle, which is Galois invariant over the algebraic closure, and you send it to the Severi-Brouwer variety that the variety X embeds into, or the class of the Severi-Brouwer variety in the Brouwer group. And so that seems like it could work. So what is the thing? So that's basically asking, can we find a line bundle on X? So if we had something in here, so if we had a central symbol algebra, it gives us a class in the Brouwer group. And it's trivial if, well, if it comes from an element which is in the image of pic X, so if it comes from a line bundle defined over X itself. So maybe we can leverage that to get some kind of algorithm. So what would the leverage be? I mean, effectively, it's kind of all the same thing. So, we would know that the central simple algebra is kind of, or at least the Brouwer class defined by the central simple algebra. It's kind of gotten from like a Galois descent of the projectivization of the space of global sections of some line bundle. And then we want to know if that line bundle is actually defined rationally. Does that have any promise? So I was a little bit hopeful just because of these kind of exact sequences here. Thinking that this map, I think is computable actually, to some extent. I don't know if you need to know a priori how to describe elements in here. So for the second part, blah, 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 using the morphism of exact sequences, we obtain an inclusion of short exact sequences. Yeah, this would rely on kind of varying over varieties X, right? We would have to know some varieties that lie on or map to the Severi-Brouwer variety of our algebra. Or we'd have to know kind of varieties such that our algebra becomes trivial once we extend to the function field of those varieties. Is that something that's manageable? There's always going to be a curve. I guess that is computable. So the equations defining the Severi-Brouwer variety I think are computable from what are they computable from? Okay, honestly, even if we could just make a variety, that would be kind of a first step. One of the problems in this field I know is like the equations defining these varieties go up in size incredibly fast. So, defining a Severi-Brouwer curve, that's just one equation. You can always define a Severi-Brouwer curve as a conic in P2. Defining a Severi-Brouwer surface is a lot harder. So you can only do that, I think, inside of like P9 or something. Last time I checked, or maybe inside of some Grassmannian. And then for 3, it's like inside, I don't know what it was, P87 or something, P81, projective 81 dimensional space. And they're not like complete intersections or anything. They're like some grotesque things. But if we could find an algorithm for giving the equations of a Severide variety, then it should be possible to pick a random hypersurface or a random equation. So a random hyperplane section of, or some number of hyperplane sections. So some linear section which gives us a curve. And then we would have for fact a curve where this guy is in the relative Brauer group. So then the question becomes, right? Yeah. So then the question becomes, like, we have this picture. We have a curve on a Severide variety, so we know that our Brauer class is in the image of such a thing. And we want to know, is there an algorithm for figuring out is the Brauer group sub-zero? Is that like the algebraic Brauer group? What is this? Just the one coming from pick 0. I think that there's a relation down here though, right? So index, the subgroup generated by the index includes in the subgroup generated by the period. It gives you this quotient. So we get pick 0 goes to pick 0k points, goes to Brauer group, goes to period mod index. So this is trivial if the period is equal to the index. It's also trivial if they're both 1. Oh shit, wait, this is a period and index of x itself. Is that a computable number? Well, probably our curve is going to have some stupidly high genus. And so this will be some finite number. Okay, this is looking not great, but still somewhat doable. So to some extent, what I think that means is that so there's a bunch of connected components of the card group of some curve, and I think that, you know, I mean, like, for an elliptic curve, there are algorithms for determining like what the structure of the torsion points is. Yeah, even for the non-torsion points, I don't know if there is such a nice algorithm. I think there's not, and we just want to know whether or not our guy came from. That's probably a bad sign. So given a map from a curve to a projective variety, is there an easy way to figure out what module is that would give you such a map? So, like, is there an easy way to figure out the linear systems from that thing? I think this answer is yes. I mean, I wonder if this is like you really can't present such a thing other than having a line bundle and some space of global sections, or some basis for that space. Megami, what are you doing? All right, I'll be right back. I think that I hate this music, but also I think that this is not the right approach to go down. I don't know if this is going to be possible. I was thinking that maybe if you just took the equations for your Severide variety sitting inside of some higher dimensional projective space, you have a linear section, which is a smooth curve. Then there's some, it doesn't matter how big of an extension it is, but there's some computable extension where so like you just pick just like any linear section of that curve, and then you look at the residues of you look at some point on that curve, right? And then over that field extension, your embedding is now an embedding into projective space. The problem is that you probably have to pick an isomorphism from projective space to the variety that curve is lying on. And then the idea was maybe, okay, let's say you could do that. Then the idea was that you have a module gotten from this map, and and this is all happening over some field extension. Maybe you can do something like compute a Galois closure for the field extension, and then ask if that module is kind of Galois invariant for the Galois group. So does the module itself come from the base field? That's actually maybe the nicest way to do this, but that relies on some hard step in the middle, right? The hard step in the middle is coming up with an isomorphism. I think this is a non-trivial thing. Isomorphism from the Severide variety to projective space. Maybe that is computable though. Maps from one projective space into another projective space. God, you gotta imagine that those are all known. Yeah, they're just some linear system, so it's just given by some collection of homogeneous polynomials all of the same degree. And so you just have to ask, like, maybe you could just go through. Okay, so one, maybe it's not so clear which degree you even need to use. I'm not sure this is a good thing to think about though. Right, so at the moment we're just trying to brainstorm whether or not there is like a possible, whether or not this is even possible. So it's totally possible that like there is no algorithm for determining the period and there's no algorithm for determining the index on classical computer. At the moment, then, this package is kind of about as far as it goes. The next thing that maybe I wanted to do was, right, so we give it essential simple algebra, and we can construct this quotient ring, which is the essential simple algebra. Maybe we could ask, given an arbitrary element inside that quotient ring, can we construct the reduced trace or the reduced norm? But that doesn't seem like a altogether useful thing. Okay, so instead of doing that, instead of thinking about this any longer, let's go start looking again at so Eric Russell has this paper, Henselian, on Brauer groups of Henselian fields. This is, I mean, this is related probably, but I don't think this was the paper that I was thinking about. I mean, this isn't the paper that I was thinking about, but I'm wondering. So one thing that I'm wondering is there is maybe this is the paper, just preprint form. Yeah, this is it. So right, so the paper computes the Brauer dimension, cyclic length, period index ratio for a tame Brauer group. And the way that it does it is it utilizes kind of an isomorphism, going from kind of the n-torsion Brauer group to kind of a space of alternating or skew symmetric matrices with coefficients in 1 over n z mod z. And okay, so when it's restricted to the n torsion in, I think that's what this is, n torsion in the kind of 2 multiple of the Brauer group, so kill all the 2's and then look at n torsion. It factors through some natural isomorphism with a wedge product, so this is the same thing but for the character group. And then wedge these are maybe just maps from F to mu n, or they're homomorphisms from the Galois group of F to mu n, which is actually what I think it is. So, the fuck is the character group? Character groups. The character group is homomorphisms from F star to F star, and this is just homomorphisms from the Galois group of the absolute Galois group of F to mu n. Is that true? It's functorial with respect to basis change, so that 2-block diagonalization on the right diagonalizes a Brouwer class. Yeah, so something that's not so clear is how do you diagonalize matrix with coefficients in here? Do you just ignore the mod z part and then diagonalize, or are there like some matrices that you have to like look at certain equivalence classes, like representatives of the equivalence class, and then try to diagonalize that? So we prove that the index of the Brouwer class is the order of the Pfaffian subgroup. Pfaffian subgroup of the skew symmetric matrix. I don't think this is supposed to be subgroup here. The order of the Pfaffian. Oh no, it probably is. It's probably like take the Pfaffian. It's going to be some subgroup in this quotient, 1 over nz mod z. And then whatever the order of that group is, that's the index. And then, and like the determinant has an explicit formula in terms of the matrix coefficients. Okay. At the same time, we show that the underlying division algebra is the tensor product of cyclic division algebras of degrees equal to the abelian group theory invariance of the row space of the skew symmetric matrix. To prove our index formula, we use valuation theoretic framework. Our methods thus generalized. So this is one thing that I wanted to... actually, 26 is his paper, probably. No? Oh, no, it's not. This is the one that I was thinking of. But it's relatively similar. Well, this one is older. So this one does the complex numbers with these variables, this iterated Laurent series field extension. And it's relatively similar. So there's an isomorphism from the Brouwer group to kind of this space of alternating matrices. And there's no worrying about kind of the characteristic of the field this time, because maybe this is all in characteristic 0. And apparently it's reducible to just some linear algebra. So there's some amount of questions about like, okay, linear algebra over Q mod Z, how computable is that? But it is promising to some extent. So I guess the next step is to read this and figure out whether or not it's possible. So we're probably just going to stop here just because it's getting late and I'm getting tired. But this will probably be where we start picking up trying to edit this this central simple algebras package. What are the problems? So one is, how are we going to even implement this field inside of Julia? So there are some constructions for like complex numbers, but the field of complex numbers is not something that's totally doable. And so honestly, like the best thing that I can think is we could maybe do it over like Q bar, join some algebraically independent guys. I mean, it's got to be stronger than algebraically independent, but some independent variables. And maybe we don't need to determine if they're independent a priori. We just have to determine if they're like a system of regular parameters. So the idea so far is this. We start with a function field over Q. You are allowed to pick a system of regular parameters and a central symbol algebra. And the goal is a central symbol algebra, which realistically you're going to define as a symbol algebra. And the goal is to take our central symbol algebra, decompose it into symbol algebras, which seemingly there's an approach to doing this in here. Once we have those symbol algebras, we try to implement the rest of this thing in order to compute the period and index. Okay, if that is even remotely possible, this would at least give us some way to take. This would at least give us some way of checking like whether or not an algebra over function field has like maximal index. We just write down the algebra. We try to run this algorithm, and if we get the degree back when we try to compute the index, then we know what the index is. Otherwise, we don't have any idea. Okay, so that's potentially the next step. Yeah. I don't know. Not optimistic. All right.